Look up on a clear day and you'll see it. A bright, endless blue sky. You've probably been told it's blue because it reflects the ocean. That's actually completely wrong. Here's a stranger fact. Sunlight actually contains more purple light than blue light. Wait, what? If there's more purple, shouldn't the sky be purple instead? That's exactly the right question, and the answer involves your own eyes lying to you a little. By the end of this video, you'll understand something about light that most people never learn. And stick around, because sunsets are about to make a lot more sense too. Let's get into it. First, let's talk about what sunlight actually is. It looks white, but it's actually made of many colors mixed together. You can see this every time a prism splits light into a rainbow. Each color in that rainbow is really just a different wavelength of light. Red light has a longer, lazier wave. Blue and purple light have much shorter, tighter waves. This difference in wavelength is the entire key to this mystery. Now, sunlight has to travel through something before it reaches your eyes. Earth's atmosphere, a thick layer of gas molecules surrounding the planet. These molecules are incredibly tiny, much smaller than the wavelength of visible light. When light hits something that small, it doesn't just pass through cleanly. It bounces off in random directions. Scientists call this scattering. And here's the crucial detail. Shorter wavelengths scatter much more easily than longer ones. This is called Rayleigh scattering, named after the physicist who explained it. Blue and purple light, with their short wavelengths, scatter far more than red or orange light. So as sunlight enters the atmosphere, blue and purple light get bounced all over the sky. That scattered light is what reaches your eyes from every direction, not just from the sun. That's the basic reason the sky isn't just black, empty space during the day. Okay, but this is where the real mystery kicks in. If purple light has an even shorter wavelength than blue, shouldn't purple scatter the most, and the sky should look purple, not blue? This is a genuinely great question, and it stumps a lot of people. The answer comes down to two separate reasons working together. Reason number one, even though sunlight contains purple light, it actually contains less of it than blue light to begin with. The sun's light output isn't perfectly even across all colors. It naturally produces more blue light than violet light. So purple starts out at a disadvantage before scattering even happens. Reason number two is the wild part. It's actually about your eyes, not the sky. Human eyes have three types of color receptors, called cones. One is most sensitive to red light, one to green, and one to blue. Notice there's no dedicated purple receptor at all. Purple light actually stimulates both the blue receptor and the red receptor a little. Your brain then blends those two signals together. And that blended signal gets interpreted as a mix of blue and white light. Combine a sky full of scattered blue light, plus a smaller amount of purple light, and your brain essentially averages it all into what we call sky blue. So it's not that purple isn't there. It's there. Your brain just doesn't render it as purple. Here's another question that trips people up. Green light sits right between blue and red on the spectrum. Why doesn't the sky look green? Green does scatter a decent amount, just not as much as blue and purple. But the bigger factor again comes back to your eyes. Our blue-sensitive cones respond very strongly to the mix of wavelengths scattered in the sky. Green gets partially absorbed into that same blended signal, without ever dominating it. The final perceived color tips clearly toward blue, not green, once everything combines. It's the same team effort as the purple situation. Physics plus biology working together. Now, you've probably also seen a sky that looks pale, white, or hazy instead of deep blue. That's not the same effect we've been talking about. It's a different kind of scattering entirely. When the air contains larger particles, like water droplets, dust, or pollution, a different process takes over, called scattering. Unlike Rayleigh scattering, scattering affects nearly all wavelengths of light fairly equally. When every color scatters about the same amount, they mix back together as white or gray light. That's why polluted or humid skies often look washed out, instead of vividly blue. More particles in the air genuinely can change how blue your sky looks on a given day. Here's a fun follow-up question. Would a camera see it differently than we do? Kind of yes. Cameras use sensors, not eyes, and they're built differently. Some specialized cameras built for scientific research can detect a slightly different color balance in the sky. But standard cameras are actually designed to mimic human color perception. So for basically every photo you've ever taken, the sky looks blue for the same reason it does to your eyes. Now let's use this same idea to explain something else you've definitely noticed. Why does the sky turn orange and red at sunset? At sunset, sunlight has to travel through much more atmosphere to reach your eyes. Compare that to the middle of the day, when light takes a short, direct path straight down. Remember, blue and purple light scatter the most easily. Over that much longer sunset path, almost all the blue and purple light scatters away before it reaches you. What's left over, arriving straight at your eyes, is mostly red, orange, and yellow light. The colors that scatter the least are the ones that survive the whole journey. That's why sunsets glow warm and orange instead of staying blue. Same exact physics as the daytime sky, just a much longer path for the light to travel. This also explains something genuinely mind-bending about other planets. Mars has a pinkish-orange sky during the day. That's not because Mars works on different physics. It's because Mars's atmosphere is full of fine reddish dust particles. Those larger dust particles scatter light differently than Earth's tiny gas molecules do. Different particle size, different scattering pattern, different sky color entirely. Same underlying idea. Totally different result, depending on what's actually in the air. So how did we even figure this out in the first place? For a long time, people had all kinds of theories about why the sky was blue. Leonardo da Vinci actually wrote about it, though his explanation wasn't quite right. It wasn't until the 1870s that physicist Lord Rayleigh worked out the real mathematics behind it. His equations precisely predicted how differently light of different wavelengths would scatter. It was one of the first times color itself was explained through pure physics and math. That's exactly why the effect is still called Rayleigh scattering today. Interestingly, Albert Einstein revisited this exact topic decades later. In 1910, he refined the math even further, connecting it to how molecules randomly fluctuate in density. It's a nice reminder that even settled science keeps getting sharpened over time. This is actually a good moment to clear up how rainbows fit into all of this. Rainbows are not caused by scattering. That's a common mix-up. Rainbows form when light refracts and reflects inside individual raindrops. Each raindrop acts like a tiny individual prism, splitting light into its full spectrum. Millions of raindrops doing this at once is what creates the rainbow arc you see. So blue sky comes from scattering. Rainbows come from refraction. Similar topic, different mechanism entirely. Quick pause before we continue. Take a guess. Do you think the sky would still look blue if humans had different eyes? Actually, no. Some animals almost certainly see the sky differently than we do. Bees, for example, can see ultraviolet light that's completely invisible to us. Their version of a blue sky might look completely different from ours. Color isn't just about the world. It's about the eyes interpreting it too. Let's clear up a few common myths before we wrap up. Myth 1. The sky is blue because it reflects the ocean. False. We just proved it's about light scattering, not reflection. Even landlocked places with no ocean nearby have a perfectly blue sky. Myth 2. Outer space is blue too, just very dark blue. Also false. Space has no atmosphere, so there's nothing to scatter light at all. That's why astronauts see a black sky even in broad daylight up there. Myth 3. The sky is technically violet, and we just can't perceive it correctly. This one's actually a fun edge case. In a strict physics sense, peak scattering does favor shorter wavelengths. But once you factor in sunlight's actual color balance and human eye sensitivity, blue is genuinely the accurate perceived result. So blue is correct. Not a compromise, not an illusion. Just the real combined result of real physics. Myth 4. The sky is blue because of the ozone layer. The ozone layer does interact with light, but it's mainly about blocking harmful ultraviolet rays, not sky color. The blue color comes from the much more abundant nitrogen and oxygen molecules scattering visible light. Myth 5. The moon has a blue sky too, just fainter. Actually, no. The moon has essentially no atmosphere at all. With nothing to scatter light, the lunar sky looks black even when the sun is shining directly on the surface. Let's wrap up with a few fun extra facts. On a totally clear day, you're technically seeing scattered light from trillions of air molecules at once. The number of molecules involved is almost impossible to fully picture. The sky also appears darker blue directly overhead than near the horizon. That's because you're looking through less atmosphere straight up than at an angle toward the horizon. Less atmosphere means less total scattering, which means a deeper, richer blue. Next clear day you have, look straight up, then look toward the horizon, and compare. You'll actually be able to see this effect with your own eyes. One last fun fact before we recap. Auroras, the northern and southern lights, get their colors from a totally different process. That's caused by charged particles from the sun hitting gas molecules high in the atmosphere. Oxygen tends to glow green or red, while nitrogen tends to glow blue or purple. So auroras are basically a totally different kind of atmospheric light show entirely. Same atmosphere, same planet, completely different physics at work. Okay, let's bring this all together. The sky is blue because of Rayleigh scattering, not ocean reflection. Shorter wavelengths of light, like blue and purple, scatter far more than longer ones like red. Purple loses out for two reasons. There's simply less of it in sunlight, and our eyes blend it into blue anyway. At sunset, light travels through far more atmosphere, scattering away the blue and leaving warm colors behind. Other planets show completely different sky colors because their atmospheres scatter light differently. And it all traces back to physics worked out over a century ago. All from one simple question nearly everyone has asked, but almost nobody has actually answered. If this answered a question you never knew you had, that's exactly what this channel is about. So if you enjoyed this, hit subscribe so you don't miss the next one. It genuinely helps this channel grow, and it takes about 2 seconds. Drop a comment and tell me which part surprised you the most. Was it the purple eye trick? The Mars comparison? Let me know. And if you liked this video, go ahead and tap that like button. It's a small click that genuinely helps this channel keep growing. There are hundreds of everyday questions just like this one waiting to be explored. Things you've seen your whole life, but never actually questioned. That's what this channel is all about. Toggling your curiosity on, one question at a time. One more thing before you go. Tap that notification bell too, so you actually see it when the next video drops. Next time, we're tackling why flamingos stand on one leg for hours without falling over. It's a surprisingly clever energy-saving trick, and you will not guess the mechanism. I'll see you in the next one.